Hello, in this video we're going to have a look at the mean and variance of a binomial distribution. So recall from advanced mathematics probability that the mean is equal to the expected value of x, which is equal to the sum of probabilities of x times p of x equals x for some values of x. The variance is also importantly equal to the expected value of x squared minus the expected value of x, which is equal to the sum of x squared p minus xp squared. Not necessarily something we have to worry about, the proofs behind those, but just keep that in mind from advanced. So we've seen in the past that the mean and variance of a Brunelli distribution was the mean was equal to p, which is the probability of success. The variance, which is that sigma squared, is equal to pq, and the standard deviation is root pq. Now, a binomial random variable where x is belonging to a binomial random variable np with n trials and the probability of p successes and q failures. The mean is actually equal to np, the variance is npq, and the standard deviation is the square root of npq. I think I've got proofs later on regarding these, but just note that a Brunelli distribution is the same as these except n is equal to 1. So example number 1 is that we've got a binomial random variable has parameters n is 20 and p is 0.1. So I might first of all say that x is a variable belonging to a binomial distribution where n is 20 and the probability of success is 0.1. So the mean, variance, and standard deviation. The mean of a binomial random variable is np, so 20 times 0.1, which is 2. So the expected value of this distribution is 2. Part B, the variance, which is sigma squared, is npq, which is just 20 times by p, 0.1, and the probability of failure would be 0.9, which gives 1.8, and the standard deviation is just the square root of 1.8, which is 1.342. Okay, let me just make this a bit smaller and move it around so I've got room. Part B, what is the probability of getting the mean when the experiment is run? So the probability of getting 2, so we want p of x equals 2. Well, there's 20, n is equal to 20, so 20 choose 2, times the probability of success is 0.1, and we want 2 of them. The probability of failure is 0.9, and we've got 18 left. So if we do that, we get 0.285. Part C, what is the probability that the result is in one standard deviation of the mean? Something that we would have seen in advanced in terms of our normal distribution, you would have looked at being within one of standard deviation of the mean. Now, if it was a normal distribution, you would just use your 65, 98, 99.7 rule, I think that is. I've never taught that one before. But the parameters are not large enough for this to be a normal distribution. Soon we're going to look at the fact that how large do our parameters have to be so that a binomial distribution becomes a normal, but in this case it doesn't quite. So one standard deviation of the mean, we're going to look above and below. So the mean is 2, so really we're looking at the probability that x is between 2 minus 1 standard deviation, which we figured out was 1.342. And then 2 plus 1.342. So we're looking at the probability that they're in between each of those. So that's the probability that it's between 0.658 is less than x, which is less than 3.342. Okay. Now, to do this question, we have to remember that a binomial distribution is discrete. And I think I mentioned that. No, I didn't mention that. A binomial distribution is discrete, which we cannot have decimal values of n. Doesn't make sense. So we're going to have to choose values of n that lie within this bound. Now you might think, oh, okay, what if I choose, this one's closer to 1, and this one is closer to 3, which is the correct answer, but the incorrect logic. What instead we chose 0 is less than x is less than 4. Let's say we chose that instead. Well, we can't actually choose that, even though they are integer values close to those decimals. 0 and 4 are no longer within these bounds. 0 is less than this bound, and 4 is larger than this bound. So you have to choose integer values that lie within the bound. So 1 and 3 does lie within this bound. So we're looking at the probability that between 1 and 3. So realistically, the probability that we're between 1 and 3 is the probability that x is 1 plus the probability that x is 2 plus the probability that x is 3. We're not going to do anything like integrate between 1 and 3 because this is a discrete distribution, which means we only have integer values of n. So the probability that we're 1 is 20. Choose 1 times by 0.1 to the 1 times 0.9 to the 19 plus 20 choose 2 times 0.1 squared times 0.9 to the 18 plus 20 choose 3 times 0.1 cubed times 0.19 to the 17. And if you do that, you get 0.745. Okay, example number 2, we've got a binomial random variable has parameters n equals 1 and p is 1 on 5. Find the mean and standard deviation. Well, the mean of a binomial random variable is equal to n times the expected value, or n times the probability of success, which is 100 times 1 on 5, which I think is 20. Yep. Now we're going to look at the standard deviation. So sigma squared is equal to npq. I meant to say variance. npq. And to find the variance, we take the square root of that. So the square root of 100 times 1 on 5 times 4 on 5. Which is 4, I think. That's cute. The standard deviation is 4. Part B says, keeping the probability of success is 1/5, what n would be needed to be increased so that the standard deviation is 1% less than the number of trials? Let's read that again, that was a bit funny. What would n needed to be increased to so that the standard deviation is less than 1% of the number of trials? So, in other words, we're saying that the standard deviation is less than the number of trials on 100. So 1% of the number of trials. Now we know that standard deviation is npq is less than the number of trials on 100. So 1% the number of trials. Square both sides, npq is less than n squared on, 10,000. But we know p and q, we actually already know what they are. So we might go n times by 1 on 5 times 4 on 5 is 4 on 25. So n times 4 on 25, and I might times the 10,000 up there, is less than n squared. Now we can cancel an n like that and say, 4 on 25 times 10,000 is 1,600. So that means n is greater than 1,600. which I think is our answer. So yeah, therefore n has to be greater than 1,600. Now, when I was first doing this question, I was thinking, oh, but isn't n 100? And I was thinking, oh, but doesn't that mean n is here 100, 100 on 100? Not quite. We're changing the value of n, and we're just looking at n, and we need to find a new value of n, so we can't use this existing value of n. That was a tricky question. Or not tricky, just confusing. Part C. Keeping n to be 100, what p must be decreased so the standard deviation is less than 1? So we want, okay, with the standard deviation being less than 1. Well, that means the square root of npq is less than 1. Square both sides, npq is less than 1. Now we want to know the value of p. So we don't know that p is 1 on 5 and q is 4 on 5. We don't know that. But we do know that n is 100. So 100 pq is less than 1. So we want to try and solve this inequality, or inequation as I say, for p. So let's get rid of q by realizing that q is 1 minus p. So this is 100p, 1 minus p, is less than 1, which means we're solving the quadratic 100p squared minus 100p plus 1 is greater than 0. Now if we use the quadratic formula, you're going to get p is equal to 100 plus or minus the square root. That's going to be what? 1,600 times 6, so 40 root 6 on 200. So if we evaluate those two numbers, so I've just used the quadratic formula there, 100 plus 40 root 6 on 100 times 2, 200, we get 0.989 ... or 0.01. So in other words, p must be changed to either 0.989 or 0.01. Interesting question, I liked it. Okay, example number 3. Two binomial random variables x and y consist of 100 Brunelli trials. For x, p is equal to q is equal to a half, so probably we're flipping a coin, and for y, p is 110. Find the ratio of their standard deviations. Okay, so let's find the standard deviation of each of these trials. We know that standard deviation is equal to, that's not a theta, it's a sigma, square root of npq. So the square root of 100 times p, which is a half, times half again, so square root of 25, which is 5. And the standard deviation of the second one, square root of 100 times 1 on 10 times 9 on 10, which you get 3. So the ratio of their standard deviations is 5 to 3. Okay, I'm going to skip those graphing ones, they're quite annoying. Example 6, finding the mean and variance of a coin being cost 100 times and the number of tails is recorded. Let's write it as a binomial distribution. So x belongs to a binomial distribution of 100, and the number probability excess is a half. So we're tossing it 100 times. We're choosing, we're looking at the variance and the mean, sorry. So the mean is equal to NP, so 100 times 0.5, so 50. So we would expect 50 heads. What that means is the mean of a binomial distribution is the average probability of success we would expect. So the mean is 50. We would expect 50 heads on average. And the variance, sigma squared, or you could say var x if you wanted to, is npq 100 times a half, which is 25. A pair of dice is rolled 120 times, and the sum of 8 is recorded as a success. Oh, that's tricky. We might have to make a little table here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Let's look at these sums. That's going to be 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. And 7, 8, 9, 10, 11, 12. So we've got 36 outcomes, and the probability of getting an 8, there's 1, 2, 3, 4, 5 of them. So this is a binomial distribution where there's 120 trials, and the probability of success is 8 on 36. No, sorry, 5 on 36. 36 outcomes, 5 eighths. So we want to know the mean, first of all, is equal to 120 times 5 on 36, which of course is, let's have a look, 50 on 3. And the variance is going to be 100 times by 5 on 36 times by 31 on 36, which is 100 3875 on 324. Okay, example 7. Find the mean, variance, and standard deviation for this binomial distribution. Well, the mean is NP, so 15 times 0.3, which is 4.5. The variance is NPQ, so 15 times 0.3 times 0.7, which is 3.15. And the standard deviation is the square root of the variance, which is 1.77. Easy. Given that x belongs to a binomial distribution, 20 experiments, 20 trials, and the probability of success is p, find, and e of x is equal to 5, find the value of p. So e of x is another way for saying the mean. So we know the mean is equal to NP. Now 5 is equal to 20p, which means p is equal to 1 on 4. Given that x belongs to a binomial distribution with n trials and p probability of success, we know the average is 9 and the variance is 6.3. Well, this is going to be, I reckon, some simultaneous equations. So 9 is equal to NP, and 6.3 is equal to NPQ. Now, we can't solve this at the moment because we've got 2 equations and 3 unknowns, but we could say this is NP, 1 minus P, which is NP minus P squared. And we know from over here that N is equal to 9 on P. So let's go 6.3 is equal to 9 on P times P, which is 9 minus P squared. So 9 minus 6.3, square root that, you get P is equal to 1. Oh, that's not right. That can't be right. Let me just backtrack here. So we've got x is a binomial distribution, average 9, and variance 6.3. Oh, yep, I know what's wrong. There needs to be another n here. Okay. 9 minus 9 on P times P squared. That and that will cancel. So we've got 6.3 equals 9 minus 9p. Let's solve for p. So 9 minus 6.3 divided by 9, we get p is 0.3. That's better. And we know that n is equal to 9 on p. So 30. Okay. Example number 10, a binomial random variable has parameters 20 and 0.1. I've done that one already, I need to scribble that out. Okay, graphing binomial distributions. If our probability of success is less than 5, our binomial distribution is positively skewed. Remember, positively skewed means the tail is pointing in the positive direction. If it's equal to 0.5, it's symmetrical, and greater than 0.5, which means it is negatively skewed. All right, that's binomial distributions. Thank you, and mean and variance.